Collisions in two dimensions. Momentum vectors, like all vectors, can be expressed in terms of component vectors relative to a reference frame. So example, if we have a reference frame here, x and y, we can take a momentum vector that is at this angle here and express it in terms of px and py. And here we're just showing the magnitudes of these components. This will also, of course, apply to 3 dimensions, but we'll just do 2 for this chapter. So that means the momentum conservation equation, where your initial momentum equals your final momentum, can be solved independently for each component. So we have p sub x equals p prime sub x, and py equals p prime sub y. Consider a system of 2 objects moving in random directions in a 2-dimensional plane and then colliding. We'll assume there are no external forces acting on the system, so momentum will be conserved. Since there is no absolute reference frame, we're free to choose one that works for us. So in this case, we'll take this as our frame, where the y-axis is in this direction, and the x we're going to line up with the velocity of mass 1. So here's our 2 objects, and we're going to assume that mass 2 is at rest just to make the problem easier. And here's mass 1, where we've lined up the reference frame, the x direction, in the same direction as mass 1's velocity. Furthermore, we're not going to assume a head-on collision, because after the collision, put a little wavy line here, m1 is going to move off in that direction. And the problem is, what's going to be the momentum of mass 2? We know that momentum must be conserved in both the x and the y directions. Initially, there is 0 momentum in the y direction. We just have mass 1 moving in the x direction. So therefore, the final momentum in the y direction must also be 0. The momentum that m1 has in the beginning will then be shared between the 2 masses after the collision. It will not be shared equally. It will depend on the masses and also the separation angle. See this angle here, m1 makes an angle with respect to the x, and then m2 we're anticipating will move something like that. Let's sketch in the vectors. Mass 1 we know moves up in that direction, so we know it has a component of momentum in this direction, which we write over here, and it also has a component in the y direction, and that's what this guy is right here. So now let's look what m2 has to do. Well, first of all, it has to make up some of this momentum. All right, this is your initial total momentum, so my final momentum has to be the same length. So this piece here is going to be due to this object here, mass 2. We also know that since there's no initial y momentum, the momentum of object 1, which is in the up direction, must be exactly canceled out by the momentum of object 2. So here's your x components, here's your y components. Let's take these blue lines here, which represent the momentum of mass 2. We add them together. Here's the horizontal component, here's the vertical component, and right here is going to be the final momentum vector for mass 2. And if you remember from just a slide back, we kind of guessed that it would move off in this direction. Educated guess. If you've ever played billiards, you would see if you hit a ball and the one ball goes this way, the other guy typically goes like that.